All righty. This is section 10. We're going to start with a series of three sections on robustness and what robustness means. This is an interesting and I think very insightful set of a series of lectures that sort of go together. So we're going to do this in pieces. Let's start with sort of what we know. Let's start with sort of the brief overview of maximum likelihood. Let's suppose I have some data. They're independent, identically distributed from some model, and that model actually has a true value. The true value is theta naught. And I want to learn, what is that true value? Well, this is pretty common setup. And so what I do is I find the log likelihood function, and I find the theta that gives me the maximum, right? So that's this thing. Put this line here. That's the point that maximizes. This is L theta hat. And I've been putting the N here just to keep track of these things. So I want to know what value of the parameter maximizes our observed likelihood function. And we write it as this. And in fact, one little piece. So this here I have the maximum likelihood estimator is the argument of theta, right? It's the parameter value that maximizes the log likelihood function, which is this point. Notice I've added in something, actually, I've added in something here, which is this 1 over n. And I think the 1 over n is helpful. It doesn't change where the maximum occurs because I'm just scaling it by 1 over n. But we recognize this 1 over n times the sum as an average. And this, of course, this last piece is going to be a consistent estimator because the log of fx is just another random variable of its expectation. So the average log likelihood will converge to its expected value. And of course, its expected value under the true model, which is why it's the expected value under theta naught. So you can imagine this as just finding the value that maximizes the average log likelihood, even in the population. But there's a relationship between the average log likelihood and something that we talked about earlier, which was the Kolbeck-Leibler divergence, and they're closely related. And so it turns out that maximizing the log likelihood is the same thing as minimizing the Kolbeck-Leibler divergence. Notice here, I have this piece here on the top and this piece here on the bottom. So to flip a log over, I have to multiply by -1, and I pulled the -1 out, which is why the max goes to the min. And then, of course, I added something here. I've added the expected value under theta naught of log f of x theta. And I can add this because it's free of theta. It has theta naught in it. It has theta naught in it, but this is fixed. This is the truth. That's a constant. And I'm not maximizing over that. So here, don't forget, I'm maximizing over theta. So really, I'm just maximizing over this bottom piece, and this is a constant which I can add on. Okay. So the key part here is that maximum likelihood can be thought of as minimizing the Kolbeck-Leibler divergence. And this is important because, and I'll draw a picture to sort of do this. Suppose I have some model space. And I know my art is fantastic, but just hang on there. So this is the model space F. All the models are here. This is, and let's say this is point of theta naught. That's the truth. This might be the point of theta 1. This might be the point of theta 2. But these are all densities. This is f of x theta. So this is the model space of densities. And what the Kolbeck-Leibler divergence is doing is it collects some data and it's picking the model that's closest to the truth, to the true point, which is this point here. That's the true point because that's theta naught. All right. And so it's telling you what model gets closest to that on average. That's what it's trying to do. let's take a look. I'm going to come back to that picture in a second, but it gives you a sense about how you might look at model spaces. And we'll get to that in a second. So what are the properties of the maximum likelihood estimator? Well, one is this nice invariance property, which is I take a function. If I'm interested in a function of the true value, I just take a function of the maximum likelihood estimator. So if I'm interested in log of the mean, I can just take log of x bar, and that's the MLE of log of mu. Nice and easy. We lose some nice things, though. Maximum likelihood estimators in general are not unbiased, right? Not. This is okay, because one nice thing that we know is that maximum likelihood estimators are consistent. That's that piece. This is that piece right here. So as n goes to infinity, and it happens at different types of consistency, and we haven't been emphasizing that in the class this year, so we're not going to worry about that too much. The way I write this precisely mathematically is I say, look, the expected value of the MLE is equal to the truth plus a little something. What is that something? That's this little something. But the something disappears as the sample size grows. So eventually I end up with just being left at the true value. One way to imagine this is we talked about these convergence things here. So imagine that this is theta naught, and I'm estimating theta naught with a biased estimator. And so my bias estimator may have a little bit of a positive bias, but the positive bias may go away. So I may get something that looks like this. And, you'll get different things. You might get somebody that comes down, you might get here, blah, blah, blah. But you eventually get a nice little cone-shaped looking thing here like this. That will eventually be set right perfect, right on the line here, right where you want to be, because the bias is going away. So you have your regular behavior that you can look at here at slices. That'll be roughly approximately normal, but you're going to have some bias, which is the distance on average. It's this distance on average from the truth. That's that BN. Okay. And that bias is going to 0. The other thing that we have that's super nice is that we have this maximum. We know that the distribution of the maximum likelihood estimators tend to be normal. All right, so that's that. And that's this piece right here. And so in large settings, you get approximate normality, okay, for the maximum likelihood estimator, where the key variance term is that information, which is the second derivative of the log likelihood that you need. And we can write this down in various ways. I think this is the easiest way. It takes a little while to get used to seeing it this way. But this is, if this were a normal distribution, this would be square root of n over 1 over sigma times x bar minus mu goes to normal 0, 1, which should look very familiar. And again, here, the truth here, we're defining this thing as the expected second derivative. And of course, I can never compute the expected derivative in practice, because in order to do that, this is taken under the true density. So in order to do that, I actually would need to know the true density, so I can't. So I'll approximate that expected value with the sample average of the second derivative. And then I'll need some value to plug in for there, and so I'll do that. All right, so we have some nice properties of maximum likelihood estimation. I'm going to go to the next page here. Turns out there are a few other things that we're not going to do, that we're not going to pay too much attention to right now. We'll touch on them later. Is asymptotic efficiency. It turns out that maximum likelihood estimators are asymptotically efficient. What that means is they attain the lowest possible variance, or the lowest possible mean square error among all comparable estimators. So they're optimal in many different in different senses. All right, and remember we had the standard notation. The log likelihood was, I could write like this, the derivative of the log likelihood function, which is the score, was here, and the second derivative, right? This is f. You can think of, well, let me not use f. This is some function. This is the function. This is the derivative. This is the second derivative, the derivative times 2, and then this is the information. Right? I have all these things right here. And we use these nice shorthands for the log likelihood, the derivative of the log likelihood score function, and the second derivative of the log likelihood, which gives us the information. So all of this theory has been developed under one important assumption, which was that the working model is the true model. So what happens when the working model is not the true model? So what happens when the data are generated according to G instead of F? We'll call G the true model and F the working model. And notice G doesn't even have a theta. There's no theta there. So it's very general. So if I assume the model has some particular form and it doesn't, what do I learn about? It's not like there's another parameter for me to learn about. I have to sort of figure out what I'm going to learn about. So the first question is, does the MLE even converge to anything if there's no true theta? The answer is, interestingly, yes, it'll converge to something. Well, how does that work now? Well, it's actually pretty straightforward if we can get through a few layers of math speak here. Essentially what you're doing is when you're maximizing the law, when you're maximizing, I don't know how to, if you're maximizing the log likelihood, right? You're actually maximizing the average log likelihood because I can multiply by 1 over n. That doesn't change anything. And the average log likelihood will converge to the true average log likelihood as the sample size gets bigger. So you're going to maximize the log likelihood in the population. How does that work? Well, let's see. When the working model fails, the MLE still converges to a point, some point in the parameter space. We're going to define what that point is in a second. We're going to call that point theta G for the moment because G is the true value. So here, what I've written is what happens. You have the maximum likelihood estimator, which by definition is this thing. It's the theta that maximizes the average log likelihood. But this is the sample average. And this thing converges to, again, same idea. The theta that maximizes, but now it's the population average. And I'm just going to define that, just defining that to be theta G. The key part here is that the sample average converges to the population average. That's the only thing that I changed. And under the population average, it's the true, right? It's the true population average. So you'll see we take the expected value with respect to G because now X is distributed G of X. So it turns out that theta G is the value of theta, okay, that minimizes the disparity between the two distributions, the model-based distributions and the true distribution. So that is theta G defines the working model that is closest to the truth. So what you're going to get is this. You're going to get the working model that's closest to the truth. When the working model is not true, you'll get the closest approximation that you could possibly get in your class of families to the true model. Well, so time out. What do you mean by close? And we can make this precise. We're going to go back to our old friend, the Kolbeck-Leibler divergence. So let's see if we can make sense of this. I'm going to I need to estimate the true model somehow. How would you estimate the true model? Well, if I wanted to know the true density, I might just have, values of X down here. And I would say, yeah, well, I saw one of those. I saw two of those. I saw three of those, four of those, one of those, two of those, three of those. So I would use a histogram. I would just plot the data. And then we might think about smoothing this thing if we wanted to, but the histogram will eventually thin out and give us a very good estimate of the truth. So I'm going to let my estimate of the true density be that histogram, which means at every X, I have mass 1 over n. It's just a histogram. Okay. And so then the height of this histogram here, this is g hat of X, which is just 1 over n times how many observations are at that point. That's it. That's the estimated probability of landing on X. It's literally just a histogram. There's a lot of little notation here, but it's pretty straightforward. And as the sample size grows, you'll get data all along the x-axis, and the estimate will end up at the true thing. All right, so why do I care about this histogram business? Well, let's take a look. The MLE is the value of the parameter that maximizes the average log likelihood function. Well, first of all, I'm going to multiply by not -1. So that flips this thing here. And then now I'm minimizing, right? So I have a -1 here and a -1 here. They cancel, they get +1. And that's why this thing is still equal to this business over here. So I'm minimizing this thing. And then I'm going to add on. So this is going to be plus a constant. And it's a constant for theta, because don't forget, I'm minimizing with respect to theta. There is no theta here. So I can just add on what I want. If I wanted to add on, I could add on 4. I could add on pi. I could add on any of these sorts of things. I don't really need to add on all those other things, but I could, because that's not going to change how I minimize this function. Function is going to be minimized at the same place. And then, of course, this piece can move on top. And so this is the argument, theta, that minimizes the average likelihood ratio. Well, okay, now wait a second. As n goes to infinity, we know what's going to happen, right? So we can write it out here. I'm going to write it out on the next page. But as n goes to infinity, this is going to be the argument that minimizes. It's going to pick the theta that minimizes the expected value of log of g of x over f of x theta, right? But it's the expected value with respect to theta, because this part here converges to that part here, because we know x is under g. So what are you doing? So actually, maximum likelihood estimation is equivalent to minimizing the Kullback-Leibler divergence between the histogram and the model. And as n goes to infinity, the histogram will go to the true density. And so you'll minimize the difference between the true density and the model. That's what's so cool about it. And what's cool about it also is that the truth can be outside of the model. Okay, so let's take a look at the next page. Let's see if I want to draw a picture here. I'll draw the picture over on this side. So when the working model fails, we need some limit theorems to apply. And this is exactly what I wrote on the other page, that the MLE converges to the thing that minimizes the Kullback-Leibler divergence. And I'm just going to define that to be theta g. Well, what does this mean? So here are the notes. The notes just write this out, just what I said. So the maximum likelihood estimator is the value of theta that minimizes the Kolbeck-Leibler divergence between the working model and the empirical density. And the maximum likelihood estimator will converge to theta G, which is the value in the model that minimizes the Kolbeck-Leibler divergence between the working model and the true density. Okay, and then if G is an F, I'm going to get the right thing. So what in the world is going on? Well, so let's go to model world. Okay, here's model world. And I drew this before. This is all the F's. So this is F of theta. So this would be F of theta naught, for example, that point. This point might be F of theta 2. These are all the models. Now let's suppose that the true model is out here in space somewhere. Well, okay, you can only pick from your data. You're going to collect data, and you're collecting data from this model. You collect data, but you can only guess. Your guess must be in the black thing. Because you're forcing yourself, you're assuming that your guess is going to be in the model. So what's the closest guess? What do you pick? Well, I would pick this point right here. That point is closest to that point. So if we let this be the Kolbeck-Leibler divergence, we're going to pick that model. The data will eventually pick that model as being the closest. That's the closest approximation. So what is that model? That is just defined to be F of theta G. That's the theta G that's closest. That's the theta. This point here, let's see, and I'm going to use a different color. This point here is the theta that is closest in model space to G. That's all that you're picking, right? So here we go. This is closest to model G in model space. And you want the point that minimizes that piece. So that's this. This is the minimization part. And this is by definition. Now, if you get lucky, let's suppose you get lucky. So let's see. Oops. So let's suppose, I'm going to get to that in a second. Let's suppose that I'm going to write over here, red equals lucky. Let's suppose you're here and this is G. Well, then you're going to end up right at the right point. You'll end up right there because the minimum divergence will be 0. And so you'll end up at F of theta G, which is in, well, let's see, which is in the model space. But since we're lucky, we're supposed to be writing in red and not green. So let me rewrite this. So this is, then you end up picking model. This is the working model equals the true model case. So you end up right where you want to be. It's pretty straightforward. And that's what number 3 says. Number 3 is this lucky case. If G is an F, right, such that G defines the truth, then theta G will just be the true point that you're looking for. Wow. Okay, this is big. Let's see how this works. Let's do some examples. All right, so if the true model is in the working space, then the maximum likelihood estimate will converge to the parameter value that indexes the true model. Okay, we know this because we just talked about it. If not, the maximum likelihood estimator will converge to the parameter value that will give you the model that is closest to the truth in terms of Kolbeck-Leibler divergence. So here's a little table. Here's your model. If the working model is true, then the maximizing parameter is this piece right here, right? If the true model is outside the model, then of course you're going to end up at that place. All right. In general, the maximum likelihood estimator will converge to theta G. theta g for theta general. That's where you end up. Theta g is the parameter that we're learning about when you look at the maximum likelihood estimator. If it happens that the true model is inside, if it happens that the true model is inside the model space, so if you have the case where you have this, and this is here, the true model's in here, then you'll get theta g is equal to whatever that true point is. If you have the case where the true model's out here, then theta g just equals theta g. You're outside here. This is theta naught. And you end up picking, whoa, sorry, I went a little too fast. Let me erase this. If that's the true model, then you end up with this point here on the edge. That is theta g. That's the point in the model space that gets you closest to the true density. All right. Okay, pretty cool. So basically all you're doing when you do maximum likelihood estimation is you're picking the model that is closest to the empirical density. You're basically model fitting the histogram. That's all you're doing. The histogram will eventually, with enough observations, give you exactly the truth. And so you're fitting your model to what the data say. And if in fact, and so you'll get the model that gives you the best fit to the data, but within the context of your model. So if your model if your model is not very flexible, then you won't have a good fit and you won't get the right parameter estimate. All right, just some terms now so that we understand, so we know. We call theta g the object of inference. This is because this is what you're learning about, okay? However, you may not be interested in theta g. I don't even know what theta g is. Right now, it's just some random theta with a subscript g. So we're going to have to calculate a couple of these and see what they are. We might not care about theta g is the point, even though we're learning about it. And that happens when our working model is not our true model. So when we want to learn about the true mean, right? I want to learn about the mean of the unknown distribution. That's what this is. Then we call that thing the object of interest. And what I would like is when the object of inference is the object of interest. And sometimes they align, sometimes they don't. So let's take a simple case. Here's a Poisson working model. The data are Poisson, usual Poisson thing. What is theta g? Well, I don't know. Well, we can actually calculate it. It's not too hard to calculate. Let's calculate the expected. In fact, let's look back here. Where's the definition? So here's the definition. So theta g is the argument right here. This is the thing. It's the argument that maximizes the expected log likelihood. Well, okay. So theta g is equal to the argument that maximizes the expected log likelihood. Okay. Well, this log likelihood is this thing. So I'm going to calculate the log likelihood on the inside, and then I'm going to pull through this expectation. And that's what I did here to the random pieces. And then I need to maximize this thing. Okay. So I'm going to take the derivative of it, and I'm going to set it equal to 0. And that only happens when theta is equal to the expected value of x. So theta g is the expected value of x. What this means is that under the working model, which is the Poisson model, right? Under the Poisson model, the object of inference, the thing that you learn about, this is what you learn about, is equal to the object of interest, which you determined already a priori, which was the true mean. So that is the parameter theta, which represents the mean of the Poisson working model, continues to represent, well, I got my things wrong, the mean even when the working model fails. I got my S's in the wrong place. Let me read it again. That is the parameter theta, which represents the mean of the Poisson working model, continues to represent the mean even when the working model fails. That is called robust. That's when you're robust. Well, let's see if it happens for other models. Let's do it again. So this isn't too bad. And basically all you're doing is you're saying to yourself, well, here's the working model. If the working model doesn't work, what do I learn about? Well, you learn about the value that maximizes the expected log likelihood, because that's what you're doing. You're maximizing the log likelihood to get your estimate. So the normal working model here is just regular old normal. I'm going to assume the variance is fixed. We all know the density. What is theta g? Well, here's the expected log likelihood. I've just wrapped some things up into the constant that I don't care about here. And then I need to find theta that maximizes this thing. And it turns out that the theta that maximizes this, you can just take the derivative and pull it through. Turns out that that thing is this, again, is the average, just like it is for the regular normal model, right? So the expected value of G, I'm sorry, with respect to X, that's this piece, is equal to this thing. So what you're learning about, okay, don't forget, X bar is your MLE in this case, right? That's equal to theta hat N. That's converging to something. What is it converging to? Well, it converges to mu if the model is correct. But the sample mean, which is your maximum likelihood estimate, is going to converge to theta g if not correct. Well, what is theta g? It just turns out to be the actual average. Now, that actual average is not mu anymore, or not theta, or I should, this is what I was thinking of as mu for here. And so you're actually just going to learn about the actual average. This is good. So here as well, the parameter theta, which represents the mean in the working model, continues to represent the mean even when the working model fails. So if you want to learn about the mean and you use the normal working model, you're in good shape, because even if the data aren't really normally distributed, you're still going to learn about the population mean. Well, that's just because X bar is that maximum likelihood estimator. So that works whether it's from a normal distribution or not. No problem. All right. So in this case, we say that both working models are robust to inferences under model failure, largely because the sample mean converges to the expected value of X, regardless of what the working model was. Here's an example where that doesn't happen. And this is common for these things. Let's look at the log normal working model. So, okay, the log normal model says, hey, I take the log of the data and then it's normal. Again, let's assume I know the variance. Okay, fine. So this is basically a normal model. Notice that I have log X in here. I got a little extra piece here to make this thing integrate to 0, but this is a log normal working model. And in this case, the average is this weird e to the mu plus sigma squared over 2. And it's weird because I'm on the log scale, so I got to go back to the original scale to make use of my parameters here. So earlier we said we were interested in the mean. So let's define theta to be the expected value of X. And then since this thing is that, I can get theta to equal mu to equal this thing. And then I'm going to take this and I'm going to plug it back in here. Okay, so I have some function of theta. Theta is supposed to be the mean, and I want to learn about the mean. So substituting this for mu, right? That's exactly what I said I was going to do. The expected log likelihood is equal to this long thing. And it's just what we saw before. It's the exact same thing as before, except I've replaced the mean here. Okay, well, I can do a little math and I'll turn out that the expected, and when I do the math, I get this piece that the expected log x of g is equal to this thing. It's equal to theta g. And then I can solve for theta g, right? And solve for theta g gives me this. So the expected value of theta g is, I'm sorry, theta g is equal E, right? This is E to the expected value of log x plus sigma squared over 2. And I can't pull the log out of the expected value because of Jensen's inequality. If I could, they'd be equal. So this is definitely not equal to this thing. All right. So if I went through this a little quick, you have a chance to go back over it. But essentially, this is a normal distribution. I rearranged the parameter so that it was a function of the mean. So I was still learning about the mean, but I'm on the log scale. So I have to go back to the original scale. That's what this piece does. So it goes back to the original scale for me. And then I take the derivative here and I set it equal to 0, right? And so then I need to find theta such that the derivative equals 0, right? That's that point. And that's this. That's all this. So you solve for theta g, and then this gives you the answer here. Now, in this case, theta g is not equal to the population mean. So this means when the model fails, the parameter we learn about ceases to be the thing we're interested in. So under model failure, the object of interest and the object of inference are not equal. So this is a bad model to use because if you have model failure, so if the log normal model is wrong, the MLE does not converge to the population average. You don't get what you want. So the first concern is when a model fails, right? And this turns out to be exactly the same. This turns out to be the same, mathematically equivalent as asking whether the model is consistent. If yes, if in fact the model is consistent under model failure, then we can worry about efficiency. That's the next piece. We'll worry about that later. The first part is understanding this. And what we did in the first part of this was, we looked to see, well, where did you converge? If you're out here, you're converging to the theta that's closest to that thing. If you're in here, then you end up at the right place. But we went a little deeper and we calculated what is theta g. And so what it turns out is that you can learn about things like the expected moment of the unknown distribution. You can learn about moments. You might even be able to learn about the second moment. But because g of x doesn't have any parameters, there's nothing really to learn about except properties of g. So what's the properties of a distribution? It would be its moments. There's no theta, there's no mu, there's no parameter. So what can you learn about? Well, you can learn about, the central moment, the second central moment. You can learn about all these different things, and that's what this is. So that's what you end up learning about. Think about it, take some time. We can do a couple examples or repeat the examples in here, work through them, and convince yourself that this makes sense. And then we'll go on to the other parts.